about how to find a volume that's rotated about the line x equals -1. I'm going to try to make it as simple as possible, but those are the two letters you're still going to want to focus on, even if you're rotating about a line that's not one of the traditional axes. Okay? Draw a picture. We'll try to make sense of it. The other one is really hard to visualize, and I'll show you some pictures of it. But we're going to deal with perpendicular cross sections. We'll get there when we get there, because I don't want to preview too much of that, because it's really weird, and my limited art abilities restrict me from being able to actually show you what it looks like. So I got a really cool program on the iPad that I'll show you. So will you do your best to graph the region that is bounded by this interesting looking function? Will you play with it algebraically to see if you can come up with what that is? And then the y-axis rotated about the line x equals 1. So will you graph that region and the line x equals -1, and we'll come back together in just a minute. Do your best to play around with the algebra to see if you can get what that function looks like. Sorry, I didn't have volume on for that, but okay. It's a semicircle, and it's weird because if it was solved for y, it would be this. Since it's solved for x and it's a y squared, it's not a function, and it's the sideways part of the semicircle, which is a little bit weird. Okay. I don't know how often you're actually going to be held accountable to that on the exam, so I wouldn't worry too much about that, but it's a nice review of a graphing skill. Okay. Then draw in your axis of rotation, which is x equals -1. And our advanced art skills yesterday said reflect over the axis, so we get this thing over here, right? And then make it three-dimensional. So you've got what kind of looks like a basketball with a cylinder taken out of the middle of it. Is that okay? Okay. Since we're revolving the region about a vertical line, we're going to need cross sections that look like this. And if my cross section looks like this, what expression is used for the height of the disk or the washer? dx or dy? dy. So we are going to integrate in the y direction. And now we need to identify what's big R, what's little r. Okay? So I'm going to go back to my picture. Okay? Big R is the distance between the axis of rotation and the outermost curve. So big R is this distance for some representative disk, right? Or some representative washer. Big R is this distance right here. What's this little distance between the blue curve and the y-axis? What's that governed by? The equation given, right? Is the radius we want more or less than that? More than that. How much more? 1 more than that. So big R is 1 plus the square root of 4 minus y squared. Make sense? We'll set up another one here if we have to in just a minute. Okay? What's little r? This one's easier. 1. Okay? Question? we're finding an area of it's not exactly a sphere. It's like a stretched out sphere with a cylinder cut out of the middle of it. If I was rotating about the y-axis, I would be making a sphere. But since I've moved the axis of rotation a little bit and taken out the middle, it's going to be, I think it's going to be a little bit bigger than a sphere. Because I've extended the radius by 1, and then I've cut out the middle. I don't know that for a fact. I just kind of get a sense. You know what I mean? Okay. So now, at this point, once you can get that picture, your work is just like you did yesterday. The volume is pi integral outer radius squared minus inner radius squared, dy. So now I just substitute in parentheses outer radius, inner radius. Bounds of integration, what do you got? -2, 2. I'm not going to spend time evaluating that, okay? Before the end of the hour, maybe we'll go over another setup of one of these with an FRQ. Would that be okay? We'll do one on your yellow packet, or do you want to do that now? We can do that at the end of the hour. Get through this other weird thing first. Okay. So similar to what we did yesterday, the weird thing is you really need to lean on your picture a little bit to determine what big R is and what little r is. Okay, this is where I fail to successfully draw good pictures. Okay, so here's I want you to read through that really quick on your own. Didn't draw that very big, but this is not what I wanted to do. That's kind of the region we're looking at, okay? This region is bounded by an upside-down parabola that's moved up 1 with a vertical shrink of 4, okay? I don't have coordinates on the axis, but you're kind of, that region okay? The cross section's perpendicular to the x-axis. So here's what's weird, and I'm going to show you this in a minute in a different way, but here's what's weird. There are cross sections that are going to jump out of the board at you, okay? And they're squares. And this is where my ability to draw pictures fails. But I'm going to attempt to do this, and then I'm going to show you a 3D model, and it's all going to hopefully come together in a way that makes sense. So we're going to have cross sections that cut the graph right there. And there's going to be squares jumping out at you, okay? How big are the squares? Well, the base of each square is a vertical distance of the function. So the base of the leftmost square is going to have this red segment as its dimension. And since it's a square, its other dimension is also that same length, right? So picture that same length jumping out of the board at you. There's a square there. It's a little bit weird, and I'm going to show you another picture that helps in a minute, okay? As I go to the right, the squares get smaller. So over here, I'm going to have a little square jumping out at you, okay? So the place where this solid is closest to you is this right over here on the left. It's got a long edge, so it's going to be the tallest away from the board. Does that make sense? And as I go to the right, the squares are going to get smaller. So the dimension gets smaller as I go to the right. So can you picture this object getting closer to the board as you go to the right, kind of? Okay. This is what, sorry, go ahead, question. Kind of an LRAM 3D, except it's not a RAM, it's a, they're squares. This is what I wanted to show you, okay? This is sine x. This isn't the function we're dealing with right now. This is sine x, and this is the same idea. The base of a solid is the curve, under the curve, y equals sine x from 0 to pi. And that blue rectangle over there on the right, represents, not a rectangle, that represents a square cross-section jumping out of the sine curve at you. Okay? And if I take this rectangle, please work. If I take this rectangle and slide it, you see how the squares, not rectangle, square, 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 square. You see how as the curve gets bigger, the square gets bigger? So this thing has like this weird shell-shaped dimension. So it's really short, and then it comes out at you, and this even gets way cooler because you can do this thing. This is the TI CAS app for the iPad. I don't know that you can get this on your school iPad, but I got it on sale. I got it at a good price. This is where it gets cool. Please work. Please work. Of course it's not going to work. There we go. Okay. So now what it's doing is as I go back and forth, it's tracing that solid. So it's a really strange shape to visualize, but it's this thing that comes out of the board at you. And if you're standing in front of the board, it's closest to you in the middle, and then it kind of tapers off. Does that kind of see where that's coming from? If you want a 3D model, it's here. That's kind of a cool way of visualizing it. This is the, if you want to see the sine curve, this is kind of where the sine curve comes from with your x and y axes there. I think it got cut off for some reason. Okay, but then you can visualize, and it's really weird, but the squares are narrower and shorter because they're squares. So the height of the square gets smaller as the length of the square gets smaller. Does that make sense? Yeah, because if it's a square, it's got to maintain length equals width. Okay, I wanted to show you one more. Here's one under a 1 over x curve. So, and your cross sections don't have to be squares. This one has a cross section that is a semicircle. So this one's even cooler. I think it makes a little bit easier picture to visualize, but you can see the taller the curve is, the bigger the semicircle coming at you. And as you go to the right, those semicircles get smaller. Here's the 3D model of what that looks like. Let's see if I can manipulate this in a way that, of course I can't do that neatly. Okay. I've kind of taken you down from like a bird's eye view of the XY coordinate plane. You see where we're at now? Okay. And I can take and I can move that. You can see, you can kind of see that yellowish cross section moving across that region. And that semicircle gets smaller as I go to the right and larger as I go to the left. So we've got kind of a, you ever wonder how trumpets are made? Kinda? You seeing a trumpet there? Trombone? No? Okay. That's kind of what I picture it as. Okay? So that's a visualization of it. That's where I wanted to go with that. Okay? It's going to tell you what shape to do. And I'll give you a couple of sample problems, but let's start with the square one. Okay? And I want to try to frame this for you a little bit. The key here is, let me draw this picture just a little bit bigger. Okay? Because I think I said this a handful of times yesterday. AP doesn't care about your drawing. You don't get points for a drawing. But the drawing is there to benefit you. So we are looking at something like this as our region. It's kind of a sideways parabola. Okay? This is the curve y equals 1 minus x squared over 4. Okay? Will you circle the word square, because I don't want to lose sight of the fact that all you're doing is finding the area of a square, and then you're going to repeatedly add together an infinite number of squares. And when you add an infinite number of squares, you're really just going to integrate the area of a square. Does that make sense? Okay? So as soon as you know it's a square, you're going to write the area of a square is whatever you think the area of a square is. You can call it L squared, you can call it W squared, you can call it whatever you want. I'm going to call this S, lowercase s squared. I'm going to say S is the side length of a square. Lowercase s squared, that's the area of a square. Now, on my picture, I need to identify what the side length of a square is. Okay? And you don't know what the side length of the square is if you picture it coming out at you. But you know what the side length of a square is if you take a cross section. If I take a cross section, the distance from the axis to the curve is a side length of a square. Does that make sense? Okay, now however long this red segment is, that's the exact same length that's going to come out at you in that third dimension. Okay? So we can identify now that the side length of a square is governed by the curve. 1 minus x squared over 4. So we take the side length of our square, or the area of our square formula, and now apply it to that. Okay? If a square is going to be turned into a volume, that square needs a little bit of thickness. What do you suppose we're going to use for the thickness of a square? We're going to use dx. I shouldn't say thickness of a square. It's really thickness of a square rectangular prism, kind of. Okay? I want to make your geometry teachers proud. I don't want to screw that up. Okay? But we're then going to turn it into a volume equation by taking 1 minus x squared over 4 squared and multiplying it by dx. So we're going to take the volume of a slice. Is that. Keep in mind, it's just the area of a square times the thickness of a slice. Okay? Then, if I've got big squares on the left and little squares on the right, and I want to add up all those squares, I'm going to turn it into an integral. So I simply put an integral in front of it. I put the area of a square times the thickness of a square in the integral, and then I have to use the correct bounds of integration. Where should I start? 0. Where should I finish? Where did you get 1? Okay, set y equal to 0. 1 minus x squared over 4 equals 0. 1 equals x squared over 4. Multiply by 4, you get 4 equals x squared. We okay here so far? What should x be? 2. A little further than 1. It should be 2. Okay? That's the volume we're looking at. What questions do you have? Should we write an integral for a semicircle one? Would that be worth it? Let's do this. The one that was shown, that I showed briefly, was y equals 1 over x, wasn't it? Y equals 1 over x looks like this. And let's go from x equals 1 to x equals 4. And let's say that the cross sections perpendicular to the x-axis are semicircles. Semicircles or semicircles? Do you care? Semicircles. Okay? So I'm going to start at x equals 1. I'm going to go to x equals 4. And there's going to be, and this is hard to visualize, but there's going to be semicircles jumping out at you. Semicircle being a half of a circle. Okay? So the key here is semicircles. What is the area of any semicircle? 1/2 pi r squared. Sorry? Okay, so what is, this gets a little bit complicated. It's not incredibly complicated. But what is, if I draw some particular cross section here, that being a semicircle, what is the radius? Half of that function value, right? So in this picture, radius is actually here. So r is half of 1 over x. Okay? So the area of a cross section is 1/2 times 1/2. Let's just call this 1 over 2x. Is that okay? Let's stick with our equation. Mr. Best, be consistent. 1/2 pi times the radius. We said the radius, we'll call this 1 over 2x squared. How do I turn it into a volume? Multiply by dx. How do I find the volume of all the semicircles added up? Integral. Integrate. What are my bounds of integration? 1 to 4. 0 is a really weird one because on this curve you can never really get to 0. So there's like an infinite volume there, which is weird. In theory, you might be able to do it. In actual practice, it doesn't make sense. Could you do it? You'd have to do it on your calculator. Yeah. Yeah. There's some cool infinite volume things. I don't know if we'll have time to get into them before the exam because they're cool. They're not necessarily useful, but there's a couple of pretty cool volume ideas that where an infinite volume isn't really infinite. Weird. Is that helpful? Another example of the same thing? Question. If it was a good question, if it was a full circle, are you saying would it be 1 over x here? Yes. If you're doing half of that, wouldn't the radius be 1 over x? We need to be careful because if we were, there are two different problems we're dealing with. Okay, I think what you could be confusing is if I use the function 1 over x and I rotated it about the axis, it would look like this. And it would have pi 1 over x squared. Because the radius is there. Okay, with this, I'm not revolving it around. I'm taking this length, and this is a really important distinction. I'm taking this length, and I'm going to have a semicircle pop out of it. So this length from the axis to the curve is actually the diameter. Does it make sense if I draw it that way? So then if I'm going to make a semicircle with that diameter, the radius has to be half of the distance from the curve to the axis. I think you were picturing this. Because if I take that and I revolve it and make it a solid of revolution, I'm always going to have a circular cross-section. So there's going to be a portion of the circle that comes out at you, and there's going to be a portion of the circle that backs into the smartboard. You know what I mean? Okay, so subtle difference. With perpendicular cross-sections, the problems that we just did, the key here is the, this isn't the one I want. I want to go down to this one. The base of a solid is flat on the paper, and there's another solid jumping out at you. Does that make sense? Okay, that's an important distinction. Okay, so I'm going to assign some book work to do, and then I'm going to actually put some FRQs on your plate too.